Hello and welcome to this AQA Further Math Statistics video, Discrete Random Variables 2, the third in the series looking at the Poisson distribution. At this video we'll be looking at what happens when circumstances mean that the value of lambda is changing. So if you read through this example here, it's one we looked at in the previous video, and we defined our random variable x as the number of cars passing a point in a road in a 5-minute time interval. And remember, with variables that follow a Poisson distribution, they are always defined for a particular time or space interval. And we are told that the Poisson parameter lambda, the average number in that time or space interval, is 4. And we needed to work out the probability in a 5-minute period exactly 2 cars went past, and that can be done on a calculator or using the formula like that, and we found that came to 0.147. So let's have a look at changing the situation that we've got slightly. So we're still trying to find the probability that exactly 2 cars go past. However, you can see quite clearly that our time interval has doubled. So x was the random variable number of cars passing a point on a road in a 5-minute time period. This time we have a different random variable where we're looking at the number of cars passing a point on a road in a 10-minute interval. And fortunately, with the Poisson distribution, the average number of events in the given time or space interval, that's lambda, is constant, fixed and finite. And that means that lambda is proportional to the time or space interval. So as our time or space interval increases or decreases, lambda is correspondingly scaled. So if we go back to this question again, we're going to define a new random variable, let's call it y, and that will be the number of cars passing a point on a road, and this time in a 10-minute time period. So our time period has doubled, so y would follow a Poisson distribution, not with lambda equal to 4, because in a 10-minute interval, double the interval, lambda would be doubled, lambda now equals 8. And if we want to find the probability this time that we have exactly 2 cars, probability that y equals 2, that would be e to the minus lambda, which is 8 this time, lambda to the power 2 over 2 factorial, and you should find that that comes to 0.107. And of course that's a far smaller probability than getting exactly 2 cars going past within the 5-minute interval. So you might want to pause a second just to read through this example. So we are starting off with defining our random variable as x, which would be the number of floors occurring in a 1-meter roll of dress material. And if you look at part A, we've been asked to work out a probability to do with the 1-meter length, and therefore if we call that random variable x, we can assume that x will follow a Poisson distribution. We can assume that floors occur at random, singly and independently, and we are looking at the number of floors per meter. And so we can model that saying x follows a Poisson distribution with lambda equal to 0.4. When we look at part B, this time we're not looking at a 1-meter length, we're looking at a 3-meter length. So let's define a new random variable y, and y will follow a Poisson distribution, but this time, because our length is 3 times larger, our value for lambda will also be 3 times larger. So lambda will now be 3 times 0.4. So y follows a Poisson distribution with lambda equal to 1.2. And finally, in part C, this time we're looking at half a metre, and so we could define a third random variable w, and again it'll follow a Poisson distribution, but this time the value for lambda will be a half of what it was originally, and so our value for lambda is going to be 0.2. And to work these out, it's fairly straightforward and you can have a go at this yourself. First of all, we want the probability that we have no floors in 1 metre, so e to the minus lambda multiplied by lambda to the 0 divided by 0 factorial, which if you remember is defined as 1, and you should obtain 0.670 for that. For part B, we want the probability of getting exactly 1 floor in 3 metres, so lambda is scaled up to 3 times 0.4, and that would be e to the minus 1.2, 1.2 to the power 1 over 1 factorial, and that you should obtain 0.361. And finally, our variable w, where we're looking at a half a metre length, so we've halved the original value for lambda, and we want the probability of obtaining exactly 1 floor, and so that would be e to the minus lambda, lambda to the 1 over 1 factorial, and that's 0.164. So rather than scaling, if we look at adding Poisson variables, if we have 2 variables x and y, each distributed with a Poisson distribution, x with parameter lambda and y with parameter mu, so we need to call it something different. Provided x and y are independent, then x plus y will also follow a Poisson distribution, and the parameter will be the sum of the 2 previous parameters. And this is fairly intuitive, so if the number of cars passing a particular point in a 5-minute interval followed a Poisson distribution with lambda equal to 4, and the number of vans and lorries passing followed a Poisson distribution with lambda equal to 2, then the number of vehicles, cars, lorries and vans that passed a particular point on a road in a 5-minute interval would be distributed with a Poisson distribution, and this time lambda would be 6. So if we have a look at a little example here, we have 2 Poisson variables here. They're independent. We want to work out the probability that x plus y equals 3. So first of all, we know that the distribution of x plus y is also Poisson, and we know that the parameter is the sum of the 2 previous parameters. So x plus y follows a Poisson distribution with parameter 1.9, and we want the probability that x plus y equals 3, so that would be e to the minus 1.9 multiplied by 1.9 to the power 3 divided by 3 factorial. And using that formula you should obtain the answer 0.171. And if you want to, you might like to just stop and check this by working out how we could obtain x plus y equals 3 using just the normal probability rules. And of course we could have, you're having a look at them here, x is 3, y is 0, x is 2, y is 1, x is 1, y is 2, x is 0 and y is 3. And you could calculate each of those and add them together and just check that the answer we got by changing and scaling our value of lambda actually does give you the same answer as going through all the possible outcomes. And that concludes this video.